So our next speaker is Sanjeeb Dash from IBM Research, and he will talk about integer programming to learn causal structures.
Well, thank you, Bartolomeo, for inviting me to speak here. So I've been here many times in the past. I've worked with, I'm currently working with both Bartolomeo and Amir Ali on some polynomial optimization work. And one of my many visits, I was actually introduced to some of these problems by talking to another professor in Orphi, Han Liu. He's left Orphi and he's now, I think, went to Alibaba maybe, then now Northwestern. But anyway, he introduced me to this problem. And so I'll talk about some of the work we've done and ongoing work on this topic. And this is joint work with Ray Chen, who was a summer intern with us, who worked on this, Tian Gao and Joao Gonçalves, who are my colleagues at IBM Research. So I'll introduce the problem of Bayesian network structure learning. For those who study statistics, it might be pretty well known. They might know many of the details well, but for people in other areas, especially integer programming, I would like to introduce some of the basics before I talk about the specific problem we're trying to solve and the integer programming methods. So the basic idea of a Bayesian network is that you have a graph. The nodes represent some random variables. You have directed edges. And these edges represent some sort of a conditional probability relationship, which I'll define more formally. So in particular, if I have a directed acyclic graph, and people, and it's not just directed graph, people use usually directed acyclic graphs when they talk about Bayesian networks. So any random variable, so once you have this directed graph model, what you do is that you claim that any random variable is conditionally independent of all its non-descendants given its parents. So those are the sort of conditional independence relationships you want to encode, but there are many alternate encodings of alternate properties which define Bayesian networks, and one of them is this basic factorization, which I will formally define in the next slide. If you assume such a graph explains a model, then you're also assuming that the joint probability distribution is getting factored in this particular way, where using the directed edges in the graph. So in particular, saying the joint probability distribution equals, or the probability of these random variables having some values equals the probability of x4 given x1. There's a directed arrow from x1 to x4. x3 given x1 and x2, so directed arrows. So x1 and x2 are parents of x3, and then x2 given x1, because directed arrow here, and then just x1 by itself. Now, there are a lot of methods to try to find nice Bayesian networks, nice as in they fit the data well. So you're given some data, and I'll explain the form in which I'll assume data is given. And there are many methods to find Bayesian networks which fit the data well, and these are some of the methods I talk about. They try to find an optimal solution, so they're just not trying to do a heuristic fit. These are all methods which try to return an optimal solution, including an integer programming based method, which is one of the state-of-the-art methods for this problem, which is also one of the reasons I got interested in this. I come from a background in discrete optimization and integer programming. So here's a formal definition of the association of the graph with the probability distribution factorization. So if you have random variables x1 to xn, you have a directed acyclic graph defined on a graph with the nodes represented by or labeled by x1 to xn. Then the probability distribution factorizes joint probability distribution in this way. It's a product of conditional distributions where you're taking each node given its parents in the graph. And so this is an assumption. So each graph, so the question is, there are many different graphs which can be defined in a collection of nodes. Which one fits the data well? Whenever you take a particular graph, you're essentially creating a model where you're making this assumption that it factorizes this way. So you can think of the graph as encoding this factorization. So let's give a simple example. Suppose I have an example on movie ratings, and you have 4 variables, the era maybe, decade, I should have probably said decades here, so 1930s, 40s, etc. till 2020s, 10 different possible values. So this is a discrete set of random variables. Then you have genre, you have 5 different possible values here, ratings, 1 to 5, viewers rate movies, and then maybe the color. Was it a black and white movie or a colored movie? And there are possible models. You can create multiple models where you can say, well, the rating depends on the genre. People rate different, like maybe more people like comedies versus horror movies. But the rating you might also postulate that the rating depends on the era. And so you might create different models, and you want to ask you ask which model fits the data better, explains the data better. I should say out here that even though I'm talking of arrows, they're not necessarily defining a formal cause-effect relationship. So we're talking of the Bayesian network as encoding conditional probability relationships, not yet cause-effect relationships. And I'll come to that in a slide or two. So how's the data given? So let's assume that you have a table of data. So you simply, different values of the random variables. Each data point or row represents some values, some assignments to the random variables. And then you're trying to learn, and maybe from this empirical data, you might calculate some sort of a discrete probability distribution. This row occurs twice, and so you look at all the rows, how many times they occur. You create some sort of an empirical distribution. And now, why would you care about these Bayesian networks? The reason for caring about these networks is this factorization, the existence of a factorization, allows you to do many things efficiently. The first thing is just encoding the information. So if I were to really encode the joint probability distribution on these 4 random variables, I would need to take all possible values of each of the random variables. So 10 for the first, 5 for the second, 5 for the third, and 2. And then I would get 5. I would need to have 500 distinct values to properly encode this, assuming it was not sparse, assuming the discrete distribution was not sparse. If, on the other hand, I had a factorization like this, well, I need to, for example, if I model 2, PE, just to encode the probability of, the probability distribution of E has only 10 values. I only need 10 distinct values, or to be precise, since the probabilities add up to 1, you can say 9 values. So the last probability value is 1 minus the sum of the rest. But just to be loose, you can say that, this, if I really were trying to encode the distribution or calculate the full distribution for this factorization, I only need to look for about 105 values. And as the graphs grow, there's an exponential gap between the number of values you might, especially if you have a Bayesian model with the in degree bounded, so every node has, let's say, at most 2 or 3 parents, then you need at most 2 to the in degree times the number of nodes, that much data to encode the distribution versus 2 to the n, even if you had a binary distribution. And then people often want to ask questions, given the graph, they'll ask questions, okay, what's the value of, for example, out of all the data, what's the probability that the genre equals war? Or given the rating is high, what's the probability that the movie was actually a war movie? So these sort of questions, inference questions, are facilitated by having sparse representations of the data. Now, one thing I want to mention, why I want to point out that these arrows, at least in the Bayesian networks, do not represent cause-effect relationships. Here's a trivial Bayesian network on 3 random variables. And at least in this model of encoding probability distributions with this definition, this factorization definition, you cannot distinguish between these 2 models. They represent the same model, same set of probabilistic relationships. And therefore, in general, each Bayesian network belongs to an equivalence class. There are many different graphs which actually represent, using the definition of factorization earlier, there are many different graphs which represent the same factorization of the joint probability distribution after some manipulation. So typically when you're looking for the optimal, you're actually looking for the optimal equivalence class rather than a single graph. And that's important. And that's important because in the theory of equivalence classes is well defined. There are algorithms to test for membership in an equivalence class for Bayesian networks, for structures I will talk about later, though that theory is not well defined. So now let's go to the more what people talk of causal graphs. We start postulating a cause-effect relationship. So for example, if you have, here's a simple example where if you have allergy, you might have itchy eyes. You have a cold, it causes a cough. So these are actual cause-effect relationships. A cold common cold, infection causes a cough, right? So, and here the arrows have more importance than, the direction of the arrows are more important than in the pure Bayesian case. And one common model in causal graphs is what are called structural equation models, very popular in the social science literature, and especially in psychometrics, psychology, and so on. Vast number of papers where they use structural equation models to model different situations. And it's interesting that a lot of work on this topic was actually done at Princeton, not in the university, in the Educational Testing Service based in Princeton, near Princeton or in Princeton. The organization that creates a GRE exam and so on. So they had a lot of initial work on structural equation models because they're analyzing performance of individuals in exams, intelligence, and so on, so forth. So in fact, this software, Listrel, there are two major packages people use in this area. Listrel, this was created by by people working at the Educational Testing Service, and AMOS is another one. So the idea of the structural equation model is you're not just assuming a sort of cause-effect relationship, you're assuming, so there's one particular, let's say, formalism which is popular in the social sciences, is that you assume, let's say, that each node represents a random variable which has a Gaussian distribution, and an arrow represents a relationship, a linear relationship, as in the following way. So A and B have no incoming nodes, no incoming edges. So XA is simply equal to some Gaussian, let's say, noise or some Gaussian variable, epsilon A, maybe with zero mean, standard normal variable, and XB the same. XC, however, is being caused by A and E, so you assume that there's a linear relationship with some constant times XA plus some constant times XE, and another noise term. And the same with XT. XT depends on XC and XB, and XE has no parents either. So these structural equation models are very popular, as I said before, and the goal of learning in this case is to learn both the directed edge structure and also these weights. Now the software like Listrel and AMOS, they actually take in an input graph and then they'll try to find these weights and effective the entire distribution. I should mention here that this subset of research where you assume Gaussian normal, Gaussian variables, Gaussian distribution, if you just think through this well, if XE and XA are Gaussian, so is XC. So the whole thing, there's a multivariate Gaussian distribution on these variables. So that's your assumption up front. But then the precise structure of that multivariate distribution is given through these structural equations. How do you create these causal graphs? Here's an example of someone created by hand, Foster Erotis. This was from, this Foster used to work for some large real estate company, now he's in Colombia. He created this by hand where he's trying to sort of create causal graph on when people will need to buy, and so that their realtors will just look at this graph and see if things are changing and then go target someone. Do you want to buy a house? So for example, if somebody here, so there's some death in the family, they might need to downgrade, upgrade, and stuff like that. So this was created more by just thinking through what people need and how different things affect one another. But I'm going to assume in this that we're trying to learn this from data. So there will be some table, and the table could be the movie table I talked about, or some simple abstract table, and they're trying to learn some sort of a structure from the data, assuming. So then the question is, if you're trying to learn a graph from data, you have to figure out whether it fits well, and how do you determine whether it fits well? Unfortunately, there's a large number of different metrics here. So from the Bayesian, from the statistics community, there are a lot of AIC, BIC, Bayesian information criterion, and a bunch of different scoring functions. So given a graph and the data table, they will calculate the score and tell you whether it fits well enough. And from the social sciences community, there are another set of, that's why I put them differently. They came from a different sort of origin, RMR, RMSCA, and so on. I'll explain the RMR in a second because that's very intuitive. The others are a little harder. There's various statistical reasons for choosing these, but we'll focus in our work on BIC, and I'll explain why in a second. And we also use a couple of these metrics just to make sure that our improvements over other codes is not completely a fluke. So the reason why many people look at the BIC score in this area is that BIC score has a nice decomposition. So the score, the BIC score, the big score of a DAG is a sum of scores of what I call the instars. What is an instar? It's basically any node and the collection of parents of that node, meaning parents for the nodes from which there's a directed edge to that node. So in this case, the instars are there. This decomposes into 4 instars: x4 with parent x1, x3 with parents x1, x2, x1 with no parents, and x2 with x1. So each of these instars, you can the score, the BIC, the big score of the graph decomposes into the sum of the scores of these instars. And that is directly connected to the fact that a Bayesian graph encodes factorization of the probability distribution. So if you think how the Bayesian information criterion score works, you're trying to take that factorized probability distribution, it's a maximum likelihood estimate based scoring function. You take the factored probability distribution, you apply it, so and the factor distribution directly targets each node and its parents. So you have a bunch of local distributions, you take the log of that, then you get a sum. So that's the basic reason why big scores decompose into sums of scores of these smaller pieces. So this can be then converted to a search algorithm. So rather than searching through graphs, fully formed graphs, what people do in this area, and certainly the integer programming approaches in this area do, is they start off instead with these so-called instars. They say, okay, I have a 4-node graph. What are possible instars defined on x3? The x3 with parent x2, x3 with parent x2, x1, and so on. So you have n minus 1 to the power n minus 1 possible sets of parents of x3, n minus 1 nodes to the power n minus 1 possible subsets of the n minus 1 nodes, each of them being parents. For each of those, you write down the score. Then the next thing is people are looking for sparse graphs. So they typically make an assumption that you're looking for bounded in degree instars. So bounded in degree commonly used in this area is 2, 3, 4. So then suddenly you have a polynomial number of instars. You can write down a score. So in other words, what is the big score of this? You're just looking at the data on the 3 variables x1, x2, x3 and seeing if this hypothesis that x3 is caused by x1 and x2 really fits the data well. And you come up with a score to measure the quality of fit. So that's what I'm calling here C3, cost of, a 3 with parents 1, 2, you get a score or a cost. And now you try to, so as I said, you calculate the score of each of these instars from data. And now you create, so the mixed integer programming approaches for this work in the following way. You enumerate a list of instars. For each instar, you calculate a score. And then you say, I'm going to select a subset of instars such that when I put them together, I do not have a directed cycle. I have an acyclic graph where the sum of the instars is as large as possible. So that's the optimization problem which people will solve in this area. And the way to do this, so then the question is, how do you write this down as an integer programming problem? And by the way, the tick marks here simply represent the optimal solution, as in these are part of the optimal graph, and the other instars are discarded by the mixed integer program. So naturally you have one binary variable per instar. And Jay wanted me to talk about binary variables. Yeah, here are the binary variables. Decision variables, whether or not you're choosing a binary variable 1 if you choose an instar to be present in a graph, 0 otherwise. What sort of constraints will force an acyclic graph? So let's just look through this set of inequalities. So you don't have to look at all the details of this. I'd rather explain this graphically. Maybe I jumped ahead, but there's a collection of inequalities. The 2 inequalities, what they do is the following. The first one is basically saying each node has to be part of an instar as the child node. So each node must be present in the graph. One instar must be chosen for each node, where the node is a child and it has a bunch of variables. That's all this constraint is saying. This one is more complicated. This is to avoid directed cycles. Basically, what this is saying is, that, so there's a lot of work in integer programming on finding graphs on constraints to enforce avoid directed cycles. But this is a little bit more complicated because these variables are on these substructures and not on single edges. So you don't have a variable for an edge, you have a variable for this entire substructure. So what this second set of constraints says, and these are called cluster inequalities, and they're used in the software GOB and ILP. It basically says that if I have a collection of graphs and I want to avoid a directed cycle, one way to do it is there must be at least one node where all the parents of the node lie outside that set of nodes. So there is a set of nodes S such that at least one node in S has all its parents outside S. So parents intersection S is empty. And this inequality simply says one of such variables corresponding to those in stars must be true, must be 1. With this and a bunch of additional inequalities, so this is enough to define a valid integer programming problem in the sense that if you solve this to optimality, you get an optimal Bayesian network structure. But to make it efficient, additional inequalities, people add additional cutting planes, additional inequalities which to the system and then solve through a branch and bound process. So now I'll move to go ahead.
So the objective function is the sum of the scores, right?
Sum of the scores where each variable represents a single instar. So that's the notation here. I, single node, a set of parents P. So those two indexes.
With respect to the Bayesian graphs,
right.
So there it's the product of
the probability distribution has a product, but when you take the maximum likelihood estimate and take the log of that, it becomes the product decomposes into a sum. So
it's a reformulation.
It's a reformulation. So in fact, it's a reformulation in the sense that the Bayesian score does exactly that. It takes a maximum likelihood estimate, which based on the factored probability distribution becomes a product of certain terms corresponding exactly to the instars. Then in the Bayesian information criterion, you take the log of that product, and since log is maximized, is monotonic, so you maximize the log is the same as maximizing the product. So then, but once you take log of the products, you get a sum of logs, and that's exactly what's happening here.
Thank you.
And it's not just a Bayesian information criterion. There are some other scoring functions which also decompose nicely in this way. So any scoring functions that decomposes in this way can be used in this basic model. So the work we did, so this was already done in GOB and ILP, and we extended this by looking at latent variables. So what are latent variables? The term used in a previous talk was exogenous variables. That's a common term too. So the idea is that, so we looked at the previous model, let's say of causal model. You might have hidden or unobserved variables, things you cannot measure. Maybe the genes have some effect on whether a person gets both allergy and colds. But you cannot really necessarily measure the effect of someone's genes. So you might postulate that there is something which is causing someone to have both of these, but you don't know the exact effect. But you're still trying to estimate the value of this. And the thing is, if you don't observe this, then the way to capture the effect of this without directly observing this is to assume that because genes might cause both allergy and cold, there is a correlation between allergy and colds, and the correlation is represented by a bidirected edge. So that's an extension of the Bayesian framework when you have latent or unobserved variables. And so now it becomes a little bit more complicated because there are many different models you might look at, as in you might look at many types of conditions these graphs have to satisfy to be a reasonable model of the data. One common model is so-called ancestral acyclic directed mixed graph. A lot of terms, let's go through them. Mixed graph, you have both directed and bidirected edges. So that's what the directed mixed graph is. Acyclic is that you don't have a cycle on the directed edges. And ancestral is that you don't have a substructure called an almost directed cycle. So you have a bidirected edge and a directed path from one endpoint to the other. That would be called an almost directed cycle. You are not allowed to have that. That is forbidden. And then that's when you have an ancestral graph. So those almost directed cycles are forbidden. And so what we looked at in our work is this class of graphs, learning them from data when you assume you have latent variables. And we gave the first mixed integer programming formulation, a mixed integer programming formulation in the first exact score-based method to find optimal ADMG. So this was earlier work, but I'll just explain this a bit and then go on to the current work we're doing. So the reason for these ancestral graphs, there are a couple of different reasons. The first basic reason is that these directed acyclic graphs are not closed under what's called marginalization. So if you have this a node which causes other nodes, you drop that node, the remaining graph is not necessarily a good model of data. Because this node is causing C and D, so C and D are correlated, but if I just remove this, then the remaining graph is not a good model. So you really have to, when you remove this, you have to add bidirected edges. And by the way, this is what I was talking about, these ancestral graphs. You don't have directed cycles. You also do not have almost directed cycles where A and B are connected by bidirected edge, and there's a path from B going through some nodes coming to A. So, and when you look at continuous Gaussian distributions and structural equation models on the same graphs, you not only assume that there are these linear expressions connecting children to the parents, so XC is BC, AXA plus some Gaussian term, but you also have these bidirected edges represent explicit covariance terms. So if I want to specify a structural equation model completely, I would look for both weights on these edges representing these constants. For each node, I would have a sort of a noise term which would represent a normally distributed noise term. But I would also assume some covariance terms and put them all together in the matrix. So let's say B, the matrix B, the coefficients are precisely these terms, the weights on the edges. And this omega represents a covariance matrix along these bidirected edges. So there will be no terms in this covariance matrix omega for, say, A and B. So the AB term in the matrix would be 0 because there's no postulated correlation. And it's not hard to see that if you start off with these matrices representing these coefficients, the normal distribution you're trying to get is this, the joint normal distribution is precisely this quantity, this matrix. The covariance matrix of the joint normal distribution, you can build it up from the pieces in this way. And so one possible thing you can try to do in this area is to say, okay, I have a sample covariance matrix, I have a bunch of data, I compute a sample covariance matrix, and then I try to find matrices B and omega, where omega is a covariance matrix, so it's positive, semi-definite, and so on. You're trying to find such a term such that this difference is minimized according to some matrix norm. So in fact, this specific matrix norm this difference norm is called RMR in the statistical literature. Most software don't necessarily look to minimize this. I just pointed out this way to just give an explicit optimization problem you could look for, where let's say even if the structure is given, you're trying to find these matrices B and omega such that this difference is minimized. So in other words, you're trying to create a covariance matrix. So this is a covariance matrix with a joint normal distribution, which is as close to the sample covariance matrix. And now if you want to go further, you not only want to estimate these terms, you want to also decide which edges should be in the model or not. So that's a high-level problem in this area. Which directed edges should be present and which bidirected edges should be present. So as I mentioned before, there are some forbidden substructures when you're looking for graphs in this area. The most basic one was you don't want directed cycles, especially when you're thinking of causal graphs. You want an explanatory model. If A causes B, B causes A. So you instead represent that by a bidirected edge. We already talked about excluding these two classes. So you want graphs where you do not have directed cycles and almost directed cycles. So this is a bidirected edge with a path from one end to the other. A special case of almost directed cycle is Bose, two nodes connected by both bidirected edge and the directed edge. And the more complicated one is what is called they're called added graphs. They do not have substructures like this. What this substructure is a collection of nodes connected by bidirected edges, such that there's also on that set of nodes a rooted arborescence, a tree-like object with a root and directed edges coming into that root from all the other nodes. So this structure can be disallowed. So these are the different categories of forbidden structures which people try to avoid when they're looking for graphs in this area. And each of them has some statistical reason. So if you have a cycle, you have some problems. If you have an almost direct cycle, you have some other problems. So that's you're trying to exclude them. You're looking for graphs without these. So again, there's a whole bunch of different methods. There's constraint-based methods, which I will not get into, but score-based methods are the category I'm talking about, where you have an explicit function giving a score to a graph. You're trying to find a graph which maximizes that score. Hybrid methods, which combine both score-based methods and the so-called constraint-based methods. Constraint-based methods, I said I won't get into it, but just briefly, the idea is you're trying to look at each edge separately and decide whether or not you want to include it. Most score-based and hybrid-based methods are currently greedy or local search algorithms which do not guarantee an optimal solution, which is what we're trying to do in this work. Now the scoring function, you don't have to go through all the details. I put it for reference, but it's a lot more complicated than in the BIC, but I can probably explain it through a graph better. So here's an ancestral graph, no directed cycles, no almost directed cycles. The way you look at this, you first decompose the graph by looking at the components defined with the bidirected edges. So this node, no bidirected edges connected. This 3 nodes connected by these 2 bidirected edges. This one a different one, and so on. You look at these components defined by bidirected edges, connected components. And now for each of these are called districts. For each of these connected components, you look at the parents. So for example, for this one, you have this one parent, so that's the structure here. For this one, no parents. For this blue, you have one parent here. So now I've color-coded the edges in the parents of the districts with the same color. And now when you take a district and its parents, that is what's a C component. So in other words, you're generalizing this notion of a child node and its parents. You're generalizing it to say, I want to look at all nodes connected by bidirected components, bidirected edges because they're correlated, and now the parents of that correlated group of nodes is what's called a C component. And that is how the scores decompose. So the scores for an ancestral ADMG is decomposed as a sum of scores of the individual C components in the graph. So as you can see, it's a more complicated structure, but we still want to try to find a score maximizing graph. And this is a decomposition in this particular graph. This is a decomposition in terms of the C components, bidirected edge, parent, single node, and so it's a single node district. No, it's not connected by bidirected edge, and its parents, and no parents. So these 3 decompose this graph, and the score of the graph is the sum of these scores. So again, as in the Bayesian case, we try to create decision variables for these C components. And for each enumerated C component, we go to the data and calculate a score, and then try to put them together such that we avoid both directed cycles and almost directed cycles. And so there could be more C components, and we're only choosing some subset of them. And all of the ones these things are calculated from the initial tabular data. So we have a mixed integer programming formulation. So you start out with a set of C components, and typically you cannot enumerate all of them. So again, you might enumerate a bunch of C components with which are small in some way. The districts are small, the bidirected components have few nodes, and the number of parents is small. So you impose that restriction, enumerate all of those, and then you impose some basic constraints. The first constraint, all it says is that every node must be part of the district of a C component. And then we want to encode by linear constraints this more complicated constraint. It says it has no directed and almost directed cycles. And now let me explain this to this picture, what it means, how we do that. So what sort of inequalities we define. We can use cluster inequalities as before, and this was a pictorial description. So you want to avoid a directed cycle. One way to avoid a directed cycle, I already explained this in the past, that for some node in the graph, in this subset of nodes, you'll insist that that node has all its parents lying outside the set of nodes. And that's encoded in this constraint. So this we already covered, but now we want to exclude almost directed cycles. So this is an almost directed cycle, so it's more complicated. So what you say in this is that for a collection of nodes, in this case nodes 1 to 3, you either have a node with all its parents lying outside the set, or for the nodes connected to the bidirected edges, all the parents have each of the nodes out here lie outside the set. If either of these conditions is true, then you will not have an almost directed cycle. And it's not hard to see, because if you had an almost directed cycle going from, say, here to here, then this node doesn't have all its parents outside. The parent of this node is this. So in other words, if you had this almost directed cycle, and this guy has a parent x3, which violates a condition that all its parents must lie outside. So these conditions can be encoded as linear constraints, this description, and this is what we call bicluster inequalities, and we add this family of inequalities. One small point I should mention is that, to those who don't work in this area, that these are exponential families of inequalities. Because an exponential family, you cannot simply enumerate them up front. This is for all. So if I jump back even for the cluster inequalities, I sort of forgot to mention this, sorry for. So this is for every set S, a subset of the set of nodes V, you have to write this constraint. So in practice, given this exponential family, you do not actually write all of them. You start out with a small subset, and then dynamically, given a solution, and you solve the LP, and LP gives you some fractional variables. You relax these variables to be between 0 and 1. You get a set of fractional values for all these variables. And then you run a second algorithm to search for a node, search for a collection of nodes for which this constraint is violated. So you only add constraints which are violated and use a heuristic or some other process to find such from your exponential list. So it's a common procedure in integer programming. When you have an exponential list, you only take a subset. That's a good point. I don't know. It could be, it might be doable for the cluster inequalities. I'm trying to think.
Just to put the enforce constraint that you don't get that.
Right. It's probably doable, but I'm just jumping ahead to where I showed that picture. You enforce a DAG. I'm not aware of that. Yeah, that's a good question. So just give you some quick summary of some numerical experiments. So this is on the trying to find these ancestral acyclic directed mixed graphs. Broad limitation, these methods don't necessarily work very well for exact methods for graphs with more than 20 nodes. 15, 20, 25, way beyond that is hard if you're trying to get these optimal solutions. So we compared with, we looked at 20 node graphs, declared some of the variables to be latent, so remove them, remove the columns in the data, take the remaining data, and now to try to go backwards. And so what we did is we made some assumptions up front. We said, okay, let's look for single node districts, meaning a single child with a bunch of parents, up to 3 parents. And we enumerated 2 node districts, one single bidirected edge, and then some parents of the 2 nodes. And we compared with some other codes, a greedy heuristic method, and some exact constraint-based methods. And this is our model, integer programming model. This is the model, our IP model. Just to give you a set of scale of the problem, you start out with roughly 60,000 variables, even after restricting these C components to have these small parent set sizes, district sizes. It's about 60,000, which is not trivial even for these small graphs. However, there are certain pruning techniques which are known in the literature. You can use them to reduce. Doesn't take too long to do that. And the important part of this root gap is simply saying that when you ignore the integrality conditions, solve the LP is very close to the final solution. The value of the LP linear programming relaxation value is very close to the optimal integer value. So that's the percentage gap. So these problems are not too hard for this size. But now we come to the actual metrics which people use. And in this particular area, as I said, you come from the statistics literature. One of the common things you look for is structural Hamming distance. Structural Hamming distance is simply saying, there was an original graph that generated my data. I have another graph. I'm trying to see how many edges I need to change in my graph before I can go back to the original graph. How many edges I need to add or subtract or flip in direction to go to the original graph. And lower is better. In this case, this is our code. This is the mean, and this, across the different random instances is a range of performance. Generally lower is better. We do better here. And precision and recall are measuring how well you're getting the actual edges in the graph. Not how many you have to change, but how much of the edges you got back. And higher is better, and in this particular case, we did better than the competing codes. I should mention that we're not necessarily finding, even though if we're solving a integer programming problem to optimality, we're not necessarily always getting the true, the generating graph, because the generating graph might have more parents for a particular node than we can enumerate in our process. So that's one limitation. I'll finish in a minute or two. We started around 12, sorry, 11, no, 10. So 10:50, so I'll stop in a minute or two and then take questions. So currently what we're working on is, as I mentioned, there's some, the statistical assumptions will drive you towards which model you're going to use, whether you're going to use these ancestral acyclic directed mixed graph, bow-free graphs, added graphs, and many different classes. We studied, what I just talked about was for ancestral acyclic directed mixed graphs, so now we're studying for bow-free graphs. So we are only excluding a bow. How do you find an optimal solution? So again, it's not very hard to write down an integer programming formulation. However, we're working on strengthening that by adding new inequalities, and that's current work. So this is just ongoing. So I have some tables and numbers. And here I want to show a couple of different metrics. So now we're trying to find, we start out with a graph, based on, generate the weights on the edges, treat that as a structural equation model. That gives a joint probability distribution, a normal distribution. Use that normal distribution to generate data. And from the data, now we're trying to go backwards and see if we can recover the structural equation model. And so this is for example, in this table, what I'm showing is the original score, the big score, averaged across a bunch of instances, and some competing methods. In this particular case, for a bow-free graph, there are no other exact methods. So ours is the first exact method. These GBAP and ABIC are methods which are the heuristics. And all of these methods, including ours, struggle for beyond 20 nodes. So, for example, GBAP and ABIC take roughly, GBAP takes more than 2 days for a 20-node graph on 40 processors, and ABIC takes also forever. So once you go beyond 20 nodes, it's pretty hard. So that does limit to an extent the applicability of these ideas, but there are problems where people do look at small number of random variables. So as I said again, in the social sciences, you might, there might be one variable for, I don't know, in medical or social sciences, small graphs are not uncommon. 10 to 15 nodes are not uncommon. So just to show you the sort of things one looks at here, there are the big score. You can see whether you're doing better or worse than the original, whether you get close to the original, and we more or less get close to the original, and this is the delta, and the average delta. We get a tiny bit better. You can fit a little bit better. That's fine. It's not, the fact that we're getting a little better than the original doesn't mean that it's wrong. And the other competing codes get a little worse. But more importantly, ours is, there's also a standard deviation. We get a much lower standard deviation. So in this particular case, this example, we deliberately created graphs which can be found by our method. As in, we deliberately created graphs at low in degree and low district sizes, meaning few nodes connected by bidirected edges. So then, when we enumerate the C components, we know that the optimal graph can be composed of the C components we created. So which is why we get such high, high performance, low gap, the big scores. And this RMSE comes more from the social sciences community. There's another metric. We do slightly better again than the competing codes. Below 0.05 is considered good in this in the social sciences literature in terms of quality of fit. I won't get into this table anymore. So. Well, as I said, we struggle once we're trying to recover graphs we had large in degrees, because we cannot enumerate all possible C components with large in degrees. So what we instead do, we created a heuristic which said we will solve the linear programming problem, look at active C components in that, and then take those active C components, try to augment them. So rather than trying to enumerate all large C components, we only take active ones and in the LP, which LP thinks are important, and look at neighboring C components and throw them into a list, and then resolve the LP again and keep repeating this for some time, and finally go ahead and solve the mixed integer program. With this, we're still able to do better than some of these competing codes, but now ours is also a heuristic. And so we have a table. I think you can look at the slides later. I won't get into all the details. Just mention that for 20 node instances, we start struggling, as do the other codes. So so a broad open question in this area is, how do you deal with these exponential sized number of C components if you're trying to look for optimal graphs? And we don't have a good answer. But in small, sort of from an integer programming perspective or combinatorial perspective, mildly interesting question is, because in this area people look for bounded in degree graphs, bounded in degree graphs as models, well, a lot of people have studied integer programming formulations when you're looking at directed acyclic graphs, but not necessarily bounded in degree directed acyclic graphs. So that could be an area of study more from the integer programming perspective. And a detailed study was already done prior to us on various associated polytopes. One can look at that to see what other constraints, inequalities, etc. are used in this area. So with that, I would like to stop and take any questions.